Recall from the previous video that this is what a typical suspension system in a car looks like. Each of the car's wheels is attached to the car's body by a spring that is coiled around a damper. When modeling a system, a good first step is to state any simplifying assumptions and to draw a diagram that only contains the key elements of the model. For example, in our model, we will only consider the vertical motion of the car's body and wheels. We will also just consider a single wheel. This means that we will only be able to describe the vertical position of the car's body above this wheel. Later, however, if we wanted to determine the entire motion of the car's body, we could apply our model to each of the four wheels and combine the results. For our schematic diagram, we'll represent the body of the car by a mass m. Because we are only modeling a single wheel, it is reasonable to assume that the mass m is equal to 1/4 of the total mass of the car's body. We then know that the car's body is connected to the wheel with a spring and a damper. The spring has a spring constant that we'll call K, and the damper has a damping constant that we'll call B. In our model, we're going to assume that the forces produced by the spring and the damper can always be modeled using linear theory. This assumption is valid as long as the compressions and elongations of the spring are small, and as long as the relative velocity between the car's body and wheel is small. So now, how do we add the wheel to our schematic diagram? Well, we know that as the wheel goes over bumps in the road, because it is pressurized with air, it will deform as it goes over these bumps. Therefore, the wheel itself will act like a spring and also will dissipate energy. So in a more detailed model, we would have to connect the spring and damper to another mass representing the wheel, which would then be connected to another spring and another damper, which would be connected to the road. In our model, however, we will assume that the deformations of the wheel are small compared to the deformations of the spring in the suspension system. Therefore, in our model, we will assume that the wheel is a rigid cylinder. We will also assume that the wheel is always in contact with the road. With these assumptions, the changes in the vertical position of the wheel will be identical to the changes in the height of the road directly beneath the wheel. Therefore, in our schematic diagram, we can attach this spring and this damper directly to the surface of the road. Remember that this line represents the height of the road directly beneath the wheel. Also note that we have drawn the spring and damper in this parallel configuration for clarity. However, recall that the horizontal placement of the components in this diagram has no significance, since we are only modeling vertical motion. The next step in the modeling process is to assign coordinates to all of the objects that can move independently, and to specify which will be the input and which will be the output. Because we are interested in how the body of the car responds to bumps in the road, we will choose the input of our model to be the height of the surface of the bumpy road directly beneath the surface of the wheel. We will denote this by the function y of t, and as we said, this will be the input for our function, for our system, sorry. We will then choose the vertical position of the car to be the output, and we will denote it by the function x of t. In both cases, we will use the convention that both x and y increase in the upward direction. The system will be in vertical equilibrium when the spring has compressed slightly, so that the upward spring force acting on the mass balances the force of gravity pulling the mass downwards. With this in mind, we will then define our coordinate system. So that x minus y equals 0 when the system is in this vertical equilibrium. With this choice of coordinates, x minus y now represents the amount by which the spring has stretched or compressed away from this equilibrium position. Further, with this choice of coordinates, we can now ignore the effect of gravity in all future calculations. The next step in the modeling process is to write down the equation of motion describing the vertical position of the mass m. We know that the motion of the mass m is governed by Newton's second law, which says that the mass m times the vertical acceleration of the mass, x double dot, is equal to the sum of the vertical forces applied to the mass. As we can see from our diagram, there are two forces acting on the mass, one from the spring and one from the damper. Recall that based on this choice of our coordinate system, we have already accounted for the force of gravity. Let's first deal with the spring force. The magnitude of the spring force is equal to the spring constant k times the relative position between the car's body and the surface of the road, which is x minus y. Observe that when x minus y is positive, the spring is stretched, and so it will be pulling downwards on the mass. And so we need to add a negative sign to indicate that the spring will pull down on the mass when it's stretched. What about the damping force? Well, the magnitude of the damping force is equal to b times the relative velocities between the body of the car and the surface of the road, which is x dot minus y dot. Again, you can see that when x dot minus y dot is greater than 0, the damper will be getting longer and longer, and it will resist this elongation by pulling down on the mass. So again, we need to add a negative sign to indicate that when the damper is getting longer, it will pull down on the mass. Now that we have derived our equation of motion, it is convenient to put it in standard form. The standard form for this equation of motion is P of d, where d is the differential operator, times x equals q of d times y. In this form, all of the inputs are on the right-hand side of the equation, and all of the outputs are on the left-hand side. If you put this equation of motion in the standard form, we get m x double dot plus b x dot plus kx equals b y dot plus ky. In this form, we can now see that the body of the car behaves like a damped harmonic oscillator that is being driven by this forcing term on the right-hand side. Note that this forcing term is governed by the function y of t, which depends on the pattern of bumps in the road and on how fast the car is driving over them. Let's consider the forcing function y of t equals a cos omega t, which would represent a road containing a sinusoidal pattern of bumps. Although this seems like an arbitrary choice that might not be representative of the pattern of bumps in most roads, it is actually a very useful choice for two reasons. Firstly, gravel roads actually do develop a sinusoidal pattern of bumps and are referred to as washboard roads. Secondly, as you will learn later in the course, an arbitrary periodic function, y of t, can always be decomposed into a sum of sines and cosines by using a Fourier series. Because this equation is linear, if we are able to solve this equation for a single sinusoidal input with a general angular frequency omega, then we will easily be able to write down the solution for any linear combination of sines and cosines. Recall that when a damped harmonic oscillator is driven by a periodic driving force, the steady-state response will also be periodic. However, the steady-state response will have a different amplitude and phase compared to the input signal. So, the important characteristics of the steady-state output, x of t, are the gain, which we'll call g, which describes the ratio between the input and output, or between the output and input amplitudes, and the phase lag, phi. Which describes the phase difference between the input and output signals. When understanding a car suspension system, the gain is the most important property to consider, and you want to design it so that it's as small as possible. If the gain is a lot less than 1, it means that the amplitude of the car's body will be very small, even if there are a lot of bumps in the road. And it means that the suspension system will be effectively absorbing bumps. On the other hand, if the gain is greater than 1, the suspension system will have the opposite effect and will actually amplify the effect of bumps in the road. For a suspension system, the phase lag is not usually of interest because the occupants of the car can only feel the amplitude of the car's oscillations and will be oblivious to any phase lag between the oscillations of the road and the oscillations of the car's body. We have now finished our modeling process of a suspension system in a car.